The figure below shows a block of mass M that's attached to one end of an ideal spring, right here, a force constant K and natural length L. So the block here is in natural state, which means that it's in equilibrium position. The block is pushed so that it compresses the spring to 3/4. So you're gonna push to the left 1/4. So it retains a 3/4 of its natural length and then release from rest. Just as the spring has extended to its natural length L, the attached block collides with another block at rest on the edge of the frictionless table. So there's no friction. Yes, had the block not been here, it would have covered another L/4 distance. When block 1 collides with block 2, half of its kinetic energy is lost to heat. So we can see that it's not really conserved. But we can still use a formula, a conservation of energy formula, to account for this loss. The other half of block 1's kinetic energy net impact is divided between block 1 and block 2. The collision sends the block 2 over the edge of the table where it falls the distance h, vertical distance h, landing at the horizontal distance r from the edge. So you can already imagine the question will ask the projectile motion. Well, let's answer the first question. Part A, it's asking us what is the acceleration of block 1 at the moment it's released from rest, from its initial position. Write your answer in terms of K, L, and M. Okay, so we clearly know that Newton's second law can be applied. And we're focusing on the block 1, so I'll say A1. Clearly, the Hooke's law is involved, but let's be careful. It's compressed to the left by a distance of 1/4 of L. So I'm going to say for X, negative 1/4 of L. Mass M, both blocks have the same mass, and the acceleration is what we're looking for. So that's our goal. Notice how the negative multiply and become positive. And then we can divide it by L. Oops, I put the K in the wrong place. Yeah, so K times L on the top, and on the bottom you have 4M. And that's your answer. Okay, part B. If B1 is the velocity of block 1 just before the impact, show the velocity of block 1 just after the impact is 1/2 V1. Okay, so the goal of the problem is to show that V prime of 1 is equal to 1/2 V1. If it said that before impact and after the impact of their collisions, that should remind you the conservation of momentum. And there is another information you need to remember. Here, when block 1 collides with block 2, half of its kinetic energy is lost to heat. The other half of block 1's kinetic energy and impact is divided between block 1 and block 2. So we're gonna need two equations that correspond to those directions. So starting with the momentum, P1 or P initial, P final should be equal. That's what the conservation of momentum is. Just before it collide, the block 1 was moving by itself, MB1, or MB1, and after it collide, the momentum will be transferred to the block 2, some of them to block 2 and some of them to block 1 to come back. So MB1 prime plus MB2 prime. It's elastic collision. Okay, they are not being stuck after the collision. So that means now that you can divide both sides by the mass m, and that gives you v1, the velocity of block 1 before the impact is equal to b1 prime and b2 prime. Now that's not enough for us to answer this because we don't have v2 prime. So to get rid of that, we need to see this variable's relationship with either b1 prime or v1. Then let's go to that what I underlined in the direction. When block 1 collides with block 2, half of its kinetic energy lost to their heat. Okay. So kinetic energy before is now got halved. So final kinetic energy is 1/2 of initial. So initially, the block 1 before the collision was 1/2 mb1 squared is equal to, now the kinetic energy got split into both block 1 and block 2 in my other underlying sentence. So that means we get 1/2 mb1 prime squared plus 1/2 mb2 prime squared. But okay, what you need to be careful is there's a 1/2 in front, and now we can knock out the 1/2 and the mass m. So that gives us 1/2 b1 squared equals b1 prime squared plus b2 prime squared. And then you can multiply 2 on both sides. b1 squared is equal to 2b1 prime squared plus 2b2 prime squared. I'm going to call this equation 2, and I'm going to call this equation 1. And we ask ourselves, is there any way we can combine this? Yes, we can. Why don't we square this equation, the first equation, so that we can knock out some variables? So square equation 1. So in other words, b1 squared is equal to b1 prime, b2 prime. You square the entire right side. And that's going to give you b1 prime squared plus 2b1 prime, or b2 prime, and then b2 prime squared. Okay, so what can we compare this to? This new equation I'm going to call 3 and equation 2. Okay, although we can just plug it in, it's better for you to knock out both variables. For us to do that, I'm going to multiply equation 3 and watch why this is better. Because there are 2 variables on each side they can knock out. So I'm going to do 3 minus 2. So this minus that goes away. You know what? Let me just write the whole thing for you to see what's going on. Here's equation 3. I'm going to copy again the both equations so that you can see my elimination method. Okay, I'm going to subtract the entire equation. And when I do that, these 2 variables go away. I get b1 squared is equal to 4b1 prime, b2 prime. So we're almost there. This new equation 4 can be compared to equation 2 because we have both squared. So I can put this using a substitution method to b1. So equation 4 gets substituted equation 2. So 4b1 prime b2 prime is equal to, okay, it's already got square, so don't square again. And that's equal to 2b1 prime squared plus 2b2 prime squared. Alright, I can divide both sides by 2, and you get 2b1 prime b2 prime is equal to b1 prime squared plus b2 prime squared. And then I can subtract the left side. And then I can factor it out as a square. Like this. When you square root both sides, you get 0 equals b1 prime minus b2 prime. Yes, we'll just keep the positive root for now. And even if you put negative root, it's going to be equal. So b1 prime is equal to b2 prime. Now that's going to be so much easier for our equation 1. If you go back to equation 1, it's telling us that b1 prime and b2 primes are equal. So our equation 1, we said b1 equals b1 prime plus b2 prime. We can just substitute the b1 prime to b2 prime. So b1 equals b1 prime plus b1 prime. b1 equals 2b1 prime. And we just proved that b1 prime is equal to b1 over 2. So that's part B. Alright, part C. Determine the amplitude of the oscillation of block 1 after block 2 has left the table. So that means after the collision, what happened to the new amplitude of the spring mass system? Well, clearly it will be less because some of the energy got transferred over to block 2. So the new amplitude definitely gotta be smaller. If you get bigger, something is wrong. Okay, so A prime for after is our goal, and the only way we can write our answer is in terms of L, meaning variable n and numbers. Okay, so what can we do here? If you look at closely the block 1 just before it hit the block 2 and just right after. Okay, it's better for you to see right after. Just after it hit right after, meaning the one we use here, B1 prime, right after the impact. Just right after, 1/2 mb1 prime squared. Okay, right now that is the it's having the most kinetic energy. So in other words, I should say kinetic energy after the collision for block 1. This is it's retaining the maximum kinetic energy right now before the restoring force accumulates as you go toward the to the right, meaning away from this natural length L. So 1/2 mb1 prime squared is equal to, now what's that going to be? For us to find the new amplitude, you know, that whole thing is going to transfer to the spring potential energy. Okay, and I'm gonna say U prime because this is after the collision. So that means you have 1/2 K M. It's really M1, but there's no distinction between M1 and M2. So K M, I'm sorry, whoops, not M, A, the new amplitude. mu amplitude squared. We cancel that out. Now B1 prime, we saw it already. B1 squared, B1 over 2 squared, mass Ka prime squared. So we can divide both sides by K. Okay, so we get the A prime squared is equal to 1/2 V1 squared over 4K, because 2 squared is 4, and that's how I get this. But unfortunately, we can't use this formula. We cannot call this answer because we can only answer it in terms of L. So how can we get the L? Well, the L comes from before the collision. So let's look at it before the collision. Before the collision, okay, we had the spring potential energy at the amplitude, and that's going to all collide to the kinetic energy before the collision, meaning it's going to be kinetic energy before the collision. So we are not going to put the prime there. I shouldn't really say initial, but I'm going to call it final. Yes, final. So 1/2 m b squared before the collision, or mb1 squared, is equal to spring potential energy was 1/2. Okay, be careful. The L is a natural length, 3/4. So that means for you to compress to 3/4 of L, you need to compress, or for you to retain 3/4 of L, the compression was L over 4. So K L over 4 squared. Okay, that's the X, the distance it got compressed. Well, that technically should minus because you compress to the left, but if you square it, it doesn't matter. So we can cancel out the 1/2, and K L squared over 16 is equal to MB1 squared. Now, where do we see the MB1 squared? We see it on the top here. Okay, do you guys see it? MB1 squared, MB1 squared. So I'm going to replace this entire thing where M1B1 squared is, and that makes it A prime squared is equal to KL squared over 16, 1 over 4K. I'm replacing the entire blue ones. So A prime squared is equal to KL squared over 64K. K's cancel. So A prime squared is equal to L squared over 64. Now this is good because our answer is now all in terms of L. The last step is for you to just square root both sides, and you get A prime is equal to L over 8. And that's our answer. Okay, part E. Find the expression for R in terms of H, K, L, M, and G. So it's asking us how far this block to travel after the collision. So only in terms of H, K, L, M, and G. Okay, those are the acceptable variables in your answer. This is clearly a projectile motion. So let's split into X component and Y component. In the Y component, we know the position change is negative big H because the final position is lower than the initial vertical position. And then the acceleration is negative G. The time is what we're looking for. Final velocity is not our interest. And then initial velocity in the vertical position will be 0 because your blocks were only moving horizontal direction, perpendicular to the vertical. So that's going to be 0, thank God. And for the X components, we have R. Okay, we are looking for this. This is our goal. And time in both x component and y component will be equal. So if you get this t, we're gonna plug it in here. Acceleration for x direction should be 0 because there's no gravity horizontally. And the final velocity, not interested. Initial velocity in the x is going to be the b prime 2 after the collision, the speed at which the block 2 was moving. Okay, so let's first find the time here. So we need to pull out the big number 2 or big kinematic equations. Number 2 was change of y is equal to b not y t plus 1/2 at squared, ayt squared. So that y was too big, ayt squared. So this one goes 0, and delta y equals negative h, 1/2, oh, there's a negative g, t squared. So this negative and negative cancel, so you get 2h over g equals t squared, and we can square root both sides and only keep the positive root because negative time is not our interest. So t is equal to square root of 2h over g. Okay, so far that will go into our horizontal component equation, which is r equals b naught xt, or it's really delta x, but I'm gonna call it r. B naught x was really b2 prime, and that we can plug this into our t's. So b2 prime is not supposed to be in our solution because the question said we can use all these 5 variables, but we are not seeing the b2 prime. But if you remember from the part B, remember we said that we got the calculation that b1 prime equals b2 prime. So we can also put b1 prime here. So r equals b1 prime 2h over g. But still, b1 prime is not acceptable in our final answer. So how do we do this? Well, we got to go back to one of our equations in the one of our answers in the earlier problems, and see if you can spot the b1 prime in terms of like L, because we can use like L here. So right here, we got the b1 squared equals kl squared over 16m. I'm going to copy this. I'm going to copy that. And let's see if that fit in our equation. Okay, let's try this. So that was the b1. Okay. Also remember that b prime of 1 equals 1/2 b1 right here. After the impact, it was 1/2 b1. Okay, so I'm going to first put this over here and then put all these variables as a final step. So r equals 1/2 v1 square root of 2h over g, and still that's not acceptable. So I'm going to square root this equation, okay, to find out that I need space. b1 equals L over 4 square root of k over m, right? And that's going to go into where b1 is. We get the r equals 1/2 L over 4 square root of k over m, and then we can all put this together. Or you know what, I will just go step by step. All the square roots will be combined now. 2kh over mg, and then you get L over 8 equals r. Now let's double check. We use h, k, mg, L, so we are in good shape, and that should be correct answer. Alright, thank you very much for watching all this far.